In this lesson, we're going to kind of introduce this idea of continuity, which basically means is the graph continuous, or if it isn't continuous, where there's these breaks in the graph. That's kind of the biggest thing. So types of breaks we can have are holes, are asymptotes, or just basically big jumps in from one section to another. So some graphs have them, some graphs don't. But here's kind of the idea, and here's some visual connections to it, that if you're talking about continuity, continuity is basically, I think of it as I draw something, do I have to pick up my pencil at any point? Right. So if I have a hole, then I have to pick up my pencil to create the hole, or an asymptote. So here's what it's defined as, though. So f of x is continuous at any particular point. So if you're looking for a particular point, only if the limit exists and it equals the y value. So visually, the limit is approaching a certain value, but remember that for a limit to exist, or for a limit to exist, it doesn't have to actually equal this value. So you have this limit approaching the same thing, and you actually get the y value that you're supposed to get. So there would be no break in this graph. Discontinuity is going to be happening when you have typically some domain issues are kind of what you're looking for. And so if you have a limit existing, but it doesn't line up with the y value. So here you have this limit existing and it doesn't line up. And that could be because this doesn't even exist, like it's undefined at that point, or there's a point like it doesn't even line up. This value is at 2 and this value is at 1. All right, so that is known as removable discontinuity. And if you think about how at least a hole happens, is that if you have some sort of a rational function and you factor the top and factor the bottom, it happens when you cancel out maybe like the x minus ones, you cancel out a factor. And so you are removing a factor, which means you're removing a value. You're removing a point. So it's called removable discontinuity. It represents a hole. And so your other one is that if you have a limit that does not exist, or a limit that is going to infinity or negative infinity, and you have that y value or that x value is undefined, right? It causes a 0 in the denominator, which is going to be creating an asymptote. So this would be a limit not existing because you're heading in different directions, or they both could be going up, or they both could be going down. So a limit might exist, but you still have something that's undefined, which kind of connects to this same idea, but it's very different, because this could be undefined and that limit exists. This could be undefined, but the limit exists, but very, very different. This is approaching a value, this is approaching infinity. Okay, so it's helpful to kind of create a visual that might kind of line some things up for you. So this one is known as infinite discontinuity. So as you're going through this, you're looking for your continuity. First, start with, is the value that they're looking for, is it a domain issue? If it's a domain issue, then you are definitely going to have a break in the graph. Whether it's a hole or an asymptote or something else, then that's to be determined. But is it a domain issue? There's a break in the graph. Does the limit exist? Right? If the limit doesn't exist, such as this, then you also have a problem. And then in order for it to work out is basically, does the limit exist? And does it equal the y value that, like, do they line up with each other? Which is what you got going on here. Right. So if you kind of go through that list and you get to this point where that value is 10 and that value is 10, perfect. Then that graph is continuous at that point. All right. That's what you're looking for. All right. So let's do this with a visual. That we have all this graph, we have all these points, and we're using the graph below to identify the values of x on the interval from 0 to 7. Notice their parentheses. So we have our 0 and 7. 0 and 7 are not included. All right, so 0 and 7, at which f has discontinuity. There are breaks in the graph. So we're going to figure out what that is, and then we're going to define them, and we're going to give a little bit of justification of why. Right, kind of going through this idea. So as we go through this, we have at 1, right, we're going to have some discontinuity. Discontinuity at x equaling 1, right? So there is 1, and that thing has a hole. And then we have it at 2, there's another hole. And at 3, total break. Call that a jump. And then at 5. We have an asymptote. Okay, so let's name them. So hole, jump. So a hole is removable discontinuity. So we have removable discontinuity. Right, at 1, we have break them up, removable discontinuity at 2. Right, doesn't matter whether that value is there or not. There's a hole. And then jump, we have this break in the graph that's potentially coming from a piecewise function, is actually known as jump discontinuity. Why I ended up calling it that. And then 5 is going to be infinite discontinuity. So just fancy names to define these pieces. Okay, and then just a quick when you're talking about 1, if you're going to justify it, it's why this doesn't happen is because the limit exists, but it's a domain issue. There's a value that's missing. So the f at 1 does not exist. Your f at 2 does not line up with the limit f of x approaches 2, right? F at 2 exists, but it just has a y value up here. The limit has a y value here, so they don't line up with each other. And then if you're talking about at 3, your limit doesn't exist. The limit as x approaches 3 on the left does not line up with the limit as x approaches 3 on the right. All right, and then our last situation is that at 5, f of 5 does not exist. Right. So that's a little bit of an introduction to it. We're going to continue on to the next problem in a different video that's going to be talking about some algebraic stuff with maybe not necessarily a video or a visual. So see if we can do this algebraically.